that any deviation, because this is obviously stochastic, so all of these guys are stochastic, so that the deviations are just random. Yeah? So whenever the return of this asset I deviates from this relationship that we have defined here, would be completely a white noise. There would be no information behind that. So it would be just a random deviation if this guy is 0. But if this guy here in our regression equation is significantly different from 0, it means that there remains a systematic mispricing. So this return here of that stock deviates significantly from what would have been predicted by the CAPM. Yeah. So our alpha here captures the mispricing. Whenever this guy is significant, then we would conclude that the CAPM does not explain the return on that stock. And how do we assess if the mispricing is significant? So in our CAPM world, people usually assume that our errors are normally distributed, which implies that our alpha would be normally distributed as well. So what we have to do is, okay, we have to check. We know the normal distribution looks like that, and we have to check if the alpha I has a value that is either above 1.96 or below minus 1.96. Why? Because we know that these are the critical values of the normal distribution, right? We know that between minus 1.96 and 1.96 is 95% of the probability mass of the normal distribution. So whenever our alpha, when the t-statistic of our alpha is above 1.96, we would reject the null hypothesis that our alpha is 0. Yeah? You remember from statistics, under the null hypothesis, you usually assume or you test that this guy here is 0. Yeah? And you reject the null hypothesis when the t-statistic of that parameter here is above 1.96 or below minus 1.96. Yeah? Given that you have a significance level of 5%. Because on the part below minus 1.96 here, we have 2.5% probability, and above 1.96 we have also 2.5% probability. So if you have a significance level of 5%, which is common practice in finance, you would reject the null hypothesis that this guy is 0 on a 5% level whenever the value is either here on the right hand side or here on the left hand side. Yeah, when it's when the t-statistic falls in this critical interval. Then a question that might arise. So, is the CAPM actually testable? Can we actually test the CAPM? So, in order to test the CAPM, if we now go back to our little picture here, yeah. So we have the risk and the return and our efficient frontier, and here is our optimal portfolio, given that this is the risk-free rate. So we can only test the CAPM if we have the right proxy for the market factor. Yeah. So if the market factor that we use is not the real market factor, if the market factor is if the market factor would be here, if it would be below the optimal portfolio, then our proxy would be wrong. If this is the case, it would be not surprising if the alpha is also deviating. And since we don't know the optimal portfolio beforehand, so it's basically not possible to test the CAPM. Yeah. All this is just theory, okay? So it's tricky to basically to test this model, or to derive any implications based upon the alpha, because we don't know if the market factor is actually the real market factor. And there are some studies who basically compare the ex post optimal portfolio with the S&P 500. For instance, this is what you can do. So you can, because the S&P 500 is a market capitalization based index. So what you can do is, so you can take the whole time series of stocks in that index, compound the optimal portfolio ex post, and compare it with the return and risk of the S&P 500. And if you see that there's a spread, then obviously the S&P 500 is not the optimal portfolio. But then you cannot test. That basically would imply then, well, that you actually cannot test the CAPM, because the alpha would not give any implication. But anyways, of course we have to have some assumptions, and in what follows for this course, so that the basic framework is that we rely on this CAPM model. Okay, so that's basically the point of departure, because we have to start somewhere. Okay, so that's our point of departure for this course. And you remember from other classes, the Farmer and French 3-factor model, or 5-factor model, or 6-factor model. They basically add here more risk factors. So of course you can expand the CAPM as well, knowing that our market factor does not explain fully the return evolution of our stocks. What people have been doing is, okay, they have been investigating what other factors could we have, what other risk factors do we have in our stock universe, or which risk factors could we derive given the data that we have. And then of course Farmer and French figured out that size matters, or that value matters. And of course, you can expand that model, then you have more regressors here on the right hand side. But the idea is the same. You have risk factors, market risk factor or any other risk factors here that should explain the return evolution of our stocks on the left hand side. And if the model is correct that you have here, if your regressor, your risk factors capture the return on what is on the left hand side, then always this alpha here should be 0, at least on a 5% level. That's basically what all these asset pricing tests are all about. Let us now take this away . So next, what we would like to talk about are the assumptions of ordinary least squares technique, because that's the basic technique. And all the models basically that we are talking about will be based upon based upon ordinary least square. So that's the basic technique. And of course we need to define some assumptions. So let's talk about ordinary least squares. It's called OLS. Whenever I talk about OLS, I refer to ordinary least squares technique or regression technique. So if we operate with the OLS model, we assume first of all linearity. So the first assumption is linearity. What does that mean? So Well, we have on the left hand side, let's define y. yi, and yi can now be the excess return of stock I. Yeah, y can be everything. Let's just denote it as yit, yeah, which can be, yeah, the excess return of stock I at time t. And on the right hand side we have a beta 0 of asset I. We have beta 1 of asset I times our first regressor x1t plus, and so on, and we have here beta k of asset I times xkt plus epsilon I t. So what we have here, we have a linear regression model. Yeah, what we have on the left hand side, our dependent variable, yeah, is in this model explained by k regressors, yeah, and beta 1 to k measure the exposure or the sensitivity of what is on the left hand side of our yi against these regressors. Moreover, we have an intercept term which is denoted as our beta 0 in this regression framework of asset I, and we have the error term epsilon I at time t. Yeah? So we have obviously different dimensions here. Dimension 1 to k is our dimension for our regressors, and we have 1 to capital T, which is our time dimension, and we have 1 until n, which is our stock dimension. Yeah, it starts with I. Yeah, I is 1 until n, and we can also denote it like that. I, then we have here t and small k. Yeah, small k is from 1 to capital K, small t is from 1 to capital T, small I is from 1 to capital N. So that's basically our definition of our simple linear regression model. And linearity now says, okay, this model is linear in the parameters here. Linear in the parameters, and I would like to say linear in our regressors as well. Yeah? So x is not squared. You see, x is linear. It's not squared. The same is for the beta. None of the betas here is squared. Yeah, it is linear. So that's the first assumption, and we can write this model here also in matrix notation. So that's basically in the standard equation form. But we can also write this model here, and that's now important, of course. So everything what we do here, you have to write down. So we can write it down in matrix notation. So then our y vector is then looks like this. We have here y1, y2, y3, y capital T. Yeah, this is a t by 1 vector. So y is an element, it's a matrix, and it's dimension t by 1. Y element n t by 1. Or we can write, sometimes you see this notation, y is element just t by 1. Yeah, so both is valid. So our y vector looks like that. It has the dimension t by 1. And because it's I, because we have n assets, we can also give here we can say if this is our first asset, y1, then we would have here, we would denote it here as well in the vector. Yeah? So just to indicate that this is the first observation of asset I at time t is 1. That's our second observation of asset 1 at time t is 2. That's our observation of asset I at time t is 3. And the last entry here would be the observation of the first asset at time capital T. Okay? Then we have our X matrix. Yeah? We can define our X matrix as capital X, which looks like this. We have in the first column a vector of ones, yeah? Capital T ones. Our second column, we have x1 at time t is 1. Second is the second observation at time t is 2 for our first regressor. Then we have the third observation for our first regressor, and here the last, of course, it is the capital T observation for our first regressor. Then in the third column we would have the same for the second regressor, and so on. And in the last column here we would have our capital Kth regressor. Yeah? And we start with the first observation, or actually our notation is now the other way around, but it doesn't really matter. So we have here basically the time dimension, so the x1 capital K, the second observation would be x2 from capital K, and the last observation would be